As some may know, I'm Dr. Ed Taubman. I'm a primary care physician by nature. I've been doing primary care since 1979 in Lowell, Maryland. About 12 years ago, I got very interested in cancer genetics. If we have time, I'll tell you the story how I got into that. And I've done probably 500 cancer genetic consults over the last decade. And some of this was self-taught. Then I attended a program sponsored by the NCI and through the City of Hope in Dorothy, California. It was a 3-month course and by Dr. Weitzel, and that solidified a lot of the concepts that we're going to be talking about now. Today, I'm going to give a primer on cancer genetics and cancer genetic counseling in general, and then we'll move into what's changed, what's new. And a number of things have changed, a bit for the better, but there's a lot of confusion out there now. So we'll try and cut through that as best that we can. If anybody needs to reach me, cancergenedoc@onlymedical.com. I practice in Only Maryland, 301-774-5400. So the basic concept, which was always agreed upon, but now everybody, I would say, does, that cancer is a disease of our genes. 5% of cancers can be traced to a single gene that we were born with, and that strongly predisposes to cancer. 5% of cancers are likely due to a combination of genes that work together that moderately increase our risk, and 75% of cancers are considered sporadic. These are genes that have become abnormal after we were born. Now, this is the same slide that when I gave this talk 10 years ago. These numbers are shifting a bit due to increased knowledge, particularly as we test more and more genes. At the end of the day, a small minority of patients' cancers are presently known to be due to a specific genetic risk. So when they come to my office for a consult, what I tell them is, our job is to see, are you in this 5% or so group where we can find a cause? And what difference does it make? Sometimes it helps chart the future for them, but if we know the specific cause, then we can test other people in the family and then separate who truly is at risk and who truly is not at risk. We need to know the cause to do that, but most of the time, we know the cause, and even that's still true today with all these panels.
I have a quick question. So 75%, are we assuming that's environmental cause?
So down to that. So usually we would say that that's due to maybe some genetic predisposition that's under there. Maybe it's environmental. So that's always the working hypothesis. But there's a theory that it's due to bad luck, and I'll talk about that a little bit later. And that theory is postulated by Bert Vogelstein, who may get the Nobel Prize for his work in cancer causes and genetics. So he says that when he says that, people listen. So what kind of started the whole ball rolling is a fellow named Knudsen, if that's how you pronounce it, and he did work on retinoblastoma back in 1970, and I actually pulled his paper. Looks like he's actually or was or is a statistician at the NCI, and he came up with a theory that retinoblastoma, which is a rare condition in children, was due to a defect in a yet discovered gene called retinoblastoma gene, and 2 kinds of retinoblastoma that they were seeing. One in children, maybe 4 or 5 years old, who would get this tumor of their eye that started retina. And there were other cases where they were children who, some of them at birth, had a retinoblastoma, and those children were predisposed to get it in their other eye. And those children who got it earlier, got it either once and or the other eye twice, their siblings were at high risk for getting this. So he came up with the theory, statistically evolved, that what was going on is that you had two alleles. We each have, to each of our 23,000 or so genes, one copy for mom and one copy for dad. There is this hypothetical then gene called the RB gene, or retinoblastoma gene, and if one of those genes got damaged randomly, for what reason, and then the second gene from the parent got damaged randomly, you get retinoblastoma. But if you were born with a defective retinoblastoma gene, so your mutation, the perception, and randomly got a second hit, then you also get retinoblastoma, but you get it at an earlier age because you had it that much earlier in your life. And once defective alleles, your siblings would have a 50-50 chance of having it. So that really turned out to be true. And that started what we know as the field of cancer genetics. So the idea is, in general, if it's due to an inborn defect, that it's an earlier age of onset, it's one of your alleles, one of your copies is defective from conception, that you have a much greater chance of getting that cancer than somebody who did not start life with one defective gene. And you may get that cancer more than once. So if it's retinoblastoma, you may get it in one eye and then later in the other, but if it's breast cancer, you may be more predisposed to get it in one breast and the other as well. What was interesting about this is these genetic causes are often what we call syndromic. I don't really understand why. But retinoblastoma, those kids also are predisposed to sarcomas, and they are also predisposed to pineal tumors. With BA, which we know about, we'll be talking about, it's breast cancer, but it's breast cancer and ovarian cancer, and pancreatic cancer, other cancers. And with Lynch syndrome, the most common inherited cause of colon cancer, it's colon cancer and uterine cancer, and pancreatic cancer and some other unusual. Why that is, we don't know, but it tends to go with the territory of inherited cancers. Just to think about this a little bit more, here's Joan, 38 years old, recently diagnosed with endometrial cancer. This family history: grandmother endometrial cancer at age 50, paternal uncle colon cancer 48, father had colonoscopy and had some adenomatous polyps. That's history. They're not Ashkenazi Jewish. So is this person worth being referred for genetic counseling and or potentially having cancer genetic testing? Anybody? Drugs.
Yes.
A lot of drugs, yes. So definitely we said earlier, younger age makes you think of hereditary cause. That's the case. If syndromic, meaning the combination of endometrial cancer, we have two endometrial cancers, and we also have a colon cancer, so part of the syndrome of Lynch syndrome. Does it mean Lynch syndrome in this family, or just a lot of bad luck, or is it possibly environmental causes? We don't know, but it's certainly worthy of looking into further. Here's another not unusual case. So that's 30 and would like a colonoscopy because his mother was just diagnosed with colon cancer on a routine screening at age 60. Paternal father, age 79 with colon cancer. So we have two colon cancers now, one at 60, one at 79. Maternal, 34 with cervical cancer, breast cancer at 85 on the other side, and of Jewish background. So what do you think?
I'm
So if we're treating people with Lynch, we get colon cancer screening at age 25, and we screen every 1 to 2 years. So, the thing, believe that this is genetic or more sporadic.
Likely not.
We got one likely not. Anybody else?
I'll agree with sporadic because of its age.
Okay. Age.
Also, the two colonic cancers are not related, right? One is mother, the other is a paternal grandmother.
Right.
They're not
Right.
related.
Cervical cancer is usually environmental.
Yeah.
Right.
And Ashkenazi Jews,
So, for those reasons, this is likely not to be genetic. I get a time you need to go into spend more time than most of us have to look at the histories. It's not uncommon for me to get a referral, somebody who had colon cancer, and then relatives are said to have had uterine cancer. To actually get the records, a lot of the uterine cancers really aren't uterine, they're cervical cancers. The lay person doesn't know. So it often gets sold as Lynch, but then when you get into it, it's not, because it's cervical, which is virally induced. And the BRCA background, that mostly applying to BRCA. It's really not having much to do with colon cancer, at least on the genetic front in a strong way. So a quick review, BRCA-related, breast cancer-associated BRCA mutations. We say 85% lifetime risk of breast cancer, 40% lifetime risk of ovarian cancer. We've known about these mutations in the BRCA gene since the 1990s, so we know a lot about them. One important point is that we quote these high rates, 85% breast cancer risk lifetime, 40% ovarian cancer lifetime. So two things. One, the studies that showed this were weighted with people who were really high risk in tertiary medical centers. In the whole world, out in the community, there are statistics that these numbers are lower. They're really not as high as this for most people. In some families, they may be. 85%, I think, is more than likely. There are studies that look more in the community, like the BRCA mutations, maybe 40%, and 20% ovarian cancer. Now, 20% ovarian cancer risk is very important because it's 1% risk in the general population. And we have no effective screening for it. Still well worth looking for it. The other thing is when somebody comes to me for counseling and they were just discovered to have a BRCA mutation and they don't themselves have cancer and they're 60 years old and their life expectancy is another 15 years, that doesn't mean they have an 85% risk of getting breast cancer in the next 15 years. They've already made it to age 60 and didn't get it. So you have to also think about modifying this when you're talking to people based on their present age. And then BRCA cancers, the BRCA1, which just means there are different genes. The first discovered breast cancer-associated gene, BRCA1, the second discovered gene associated with breast cancer, and BRCA2. They're two different genes. Here's an important point, that in the general population, the risk of carrying this is 1 in 400 to 1 in 1,000. In the Jew population, which is most American Jews who are called Ashkenazi and came from Eastern Europe, Poland, Russia, etc., it's 1 in 40. So if we just walk through the hospital and just pass people in this, who are walking down there, we're going to run across somebody who's BRCA positive and probably doesn't know it. There's a lot of this out in the community. One can make a case for testing, offering testing for all people of Jewish descent. That happens. And the BRCA mutations, this is just a quick understanding of it. Here's two genes, the BRCA1, the BRCA2. The BRCA2 is a larger gene. The Jewish, here's, and this is an old slide, but here are various variations / mutations where a change in the spelling can lead to high risk of breast cancer and ovarian cancer. So lots of different places in these genes where just a single change in a genetic letter can lead to these syndromes. In breeding, or we call a founder mutation in the Jewish population, there are commonly these three. So back in the day when we started doing this, we offered 3 sites for peoples of Ashkenazi descent. But in any population, whether Ashkenazi or not, other deleterious variations can be present. Does that make sense? I'm going to show a family, a woman who had ovarian cancer at age 62. There's nobody else in this family who has any cancer. Is this appropriate for genetic counseling testing? I'm going to have Eric give the answer because he knows.
Yes.
Anybody here?
It came from God. Did you hear that?
Came from God? God, yes.
No.
Anybody know?
Variant. Any variant.
Any other? So
Oh, really?
this case, actually, I gave a grand rounds on cancer genetic testing about 7 years ago at one of the hospitals. And, afterwards, the doctor came up to me and said, my wife had cancer at age 62, but there's nobody else in the family who has any cancer. What do you think? And as was just chimed in, 2 reasons to test in this family. And this is a paper through Dr. Whitesell's group. That's where I did my City of Hope training. And basically, they said if you have what we call a limited family history, in other words, there are very few women in the family, you don't have any sister aunts, for instance, that's a potent risk factor in setting of BRCA, because we have a lot of people who didn't have it to say that it's not present. But actually, not having other women in the family is one of those potent risk factors to look at. It's potent or more potent than being of Ashkenazi descent. That's one article. This is another article in which I think this is done through Moffitt, where they test all people, regardless of ethnicity, for BRCA mutations who have ovarian cancer. And at the time, surprisingly, about 15% of the ovarian cancer, regardless of their ethnicity, had a BRCA mutation. So you look at this family, you have cancer, risk regardless of your ethnicity, and got a brother but no sisters. Okay, and she doesn't have any aunts on the paternal side. Remember, these mutations can come in the paternal side. Tested this person, they had a mutation. Well, that's important because there are 3 daughters in here, and to know that so they can be proactive. Colon cancer. So same kind of pie chart. This was a slide that's about 10 years old. Again, we have a lot of sporadic. We don't know the reason. Here's Lynch syndrome. We were starting to check for some other genes scattering in there, and then see clusters and families of familial. But what causing is familial and sporadic? Well, it says here, as yet undiscovered hereditary cancer variants. So because if we keep looking, we'll find more and more genetic causes, and then this sporadic will start getting less of the pie, and the known genetic causes will be more. So that's really true. Yes and no. Henry Lynch, the fellow who got the ball rolling for the genetic causes of colon cancer, we now it's the name HNPCC, hereditary non-polyposis colon cancer, which he really got the ball rolling on. It's now named after him as Henry Lynch. It's called HNPCC. It's the most common hereditary cause of colon cancer. It's a minority of colon cancer. And it goes by HNPCC. Previously, hereditary non-polyposis, there really are polyps involved. There are just not that many of them. And the difference with Lynch syndrome is when you get polyps, they can more quickly go on to colon cancer. Hence, that's why it's like colon cancer predisposition on steroids. So it's not the number of polyps in Lynch. There may be very few, but when you get them, they can quickly go on through progressive genetic instability, those polyps become cancerous. And hence, that's why we start screening when we know it's Lynch syndrome. It's suspected at age 25 and every 1 to 2 years for colon cancer. Because if you wait the usual 5, 7, or 10 years, by the time a polyp develops, you may miss the opportunity to catch it. What are the genes? The usual ones are H1, MSH2, MSH6, PMS2. In the recent years, there's another gene called EpCAM, which lives just north of the MSH2 gene, and when it's defective, it affects the function of the MSH2 gene, which is just south of it in the genome. That's the gene that can do it. And then this is one I recently heard about. This is where MSH2 is, the gene has not been mutated, it's just been turned upside down in the genome. If you do sequencing for it, there's no mutation in it, it's not going to show up in MSH2 screening. You've got the normal requisite genetic code. It's just upside down. We analyze the soup fragments, that's how they do next gene sequencing. They know whether it's upside down or right side up. They just be sequencing. So for some patients, a very small minority, who we suspect Lynch syndrome, and we suspect it's in the MSH2 gene, but we can't prove it, may want to go back, and you can now check for MSH2 inversions. And like a giant jigsaw puzzle, we've got the corner pieces, but we're a bit filling it in with things like this. And other things to think about in Lynch syndrome is that usually it's more right-sided cancer than left. There can be some unusual cancers, bile duct, gastric. Read the normal renal cancer. This is renal pelvic cancer or ureteral cancer, ovarian and pancreatic. If it's a brain with Lynch syndrome, it can be called Turcotte. If it affects a skin condition called sebaceous neoplasm condition with sebaceous cancer in conjunction with other Lynch syndrome cancers such as uterine cancer and colon, that's called Murray-Thorez syndrome, typically in the MSH2 gene. Biologist here today? Okay, there we go. So we rely in part on family history to figure out who has got Lynch syndrome. We certainly still do that. We also relied heavily on the pathologist. We had things like Bethesda criteria. And these are things we were looking for: lymphocytic infiltration, Crohn's-like reaction, signet, medullary growth pattern. Those are supposed to have the pathologist say, hey guys, let's think about that. And on the looking at pedigrees, the Amsterdam criteria, what I call the 3-2-1, which means 3 colon cancers over 2 generations and 1 less than age 50. So that's the classical way of looking for Lynch syndrome, by looking at a pedigree. And this are the first cases that I was referred to when I started doing cancer genetic counseling. So the person who referred to me was right here. This person was in their 50s, and I was seeing their gastroenterologist because they're afraid of colon cancer. Why? Because one of their brothers had cancer in their 30s and died. Nobody expecting that. And the father died of colon cancer. Another brother died of colon cancer. And the sister died of ovarian cancer. It can be part of Lynch syndrome too. And the sister's son developed colon cancer in their 20s and died of that. And the remaining sibling died not from cancer, they committed suicide. So this is it. I can't take this anymore. This is a fulminant case of Lynch syndrome. You're not going to miss this when you you should this if you get a history. The problem was, back in the day when this happened, no genetic testing was available. And a lot of potentially at-risk people over here. So this is a teaching point where this is important. And I spent some time with this case. This person over here needed to be tested because insurance wouldn't pay for testing unless there was a known mutation in the family. Well, we hadn't discovered it. At the time, genetic testing was about $5,000. They were prepared to do that. So what we did is we went in person, this young man who had died in their 20s, so at this point it was just a few years ago, and we got family to pitch in and pay for IHC testing to see if there's evidence of Lynch syndrome. That's testing on the tumor. And that helps us see whether Lynch syndrome is in the ballgame and which of the Lynch syndrome genes to look for, particularly if we're going to have to pay for it on our own, because insurance is not going to. End of the day, when the IHC testing, I'm going to talk a little bit more about this, they drop out of MSH6, which is consistent mostly with an MSH2 mutation. Once we tested this person, who's asymptomatic, by the way, and is in his 50s, and behold, that person had a known MSH2 deleterious variation or mutation. Now we know, years later, figure out the mystery of what's called all this havoc. Then I went back and probably broke every HIPAA rule that there was, but I located the wife of this now deceased person, and spoke with her, and we and she agreed to talk to her children who are teenagers, how to go and lead their hopefully healthy lives. And they came in and they got tested for the mutation. We already put the needle in the haystack, and both of them have the mutation. That's bad, but it's good because now they know what to look out for, and they're getting colonoscopies every year, and hopefully they're not going to end up like their dad did. This is why cancer genetic counseling can be important. C testing, that we look on the tumor for evidence of for Lynch syndrome. So how does that work biochemically? So we have two genes, MSH2 and MSH6, which in this cartoon pair up. They call it a dimer. And slide down looking for DNA damage. And eventually, if they find a genetic change or a misspelling, they excise it and replace it with the right letter. So MSH2 and MSH6 pair together down, and they hook up with PMS2 and MLH1. So the purples, MSH2 and MSH6, they pair, and then the MLH1 and the PMS2, they pair. They form heterodimers. And the whole complex comes down, looks for genetic damage, and excises it, which helps in cancer down the road. So on IHC testing, we're looking for evidence of whether these genes are functioning or not. As it turns out, if there's a dimer and one of these genes is their protein product is not working, and the other one degrades as well. You need both of these so that the two don't degrade. If one is not working, then they both degrade. So hence, if you have an MSH2 mutation genetically and making the requisite amount of MSH2 protein, even if you have MSH6 protein, when you look on IHC, you're going to be missing both. That's how it works. And similarly for MLH1 and PMS2, if there's an MLH1 mutation, then there's not the proper amount of MLH1 protein. When you stain for MLH1 protein, it's going to be absent in the tumor, but so will be PMS2 because this dimer is defective and both of them have degraded. So it's a screening tool on DNA, and it can be helpful for screening people. There's screening, it's called MSI by PCR. It's also good for screening for Lynch. It's with microsatellite instability, but it won't tell you which genes are causing the microsatellite instability. One of the advantages of this is it's independent of the family history. A lot of people, we live in an age where people have small families. How they their family histories, or they came from all over the world, and who knows what went on in San Salvador and in Mexico when people died. We don't know. So family histories are not always very accurate. And depending on pathology is not all that accurate either. So IC testing is a way to screen. So if you screen, well, with Lynch syndrome in everybody, we need to screen everybody. On the other hand, less than 5% of people who have colon cancer, even at age 50 and less, have Lynch syndrome. So are we going to screen everybody to get that small thing, minority, or not? That really depends on your institution and what your resources are. If IC testing is relatively inexpensive, you could have everybody, or you could just screen at age 60 or 50 or 70. You just have to do the math, figure out how you're going to do it, catch people. And there are institutions where they're screening not only the colon cancer tumors, but also uterine cancer tumors. And it's like, whoa, that's a lot of resources, money to do this. But you know what? If you pick up a person, you pick up a family, and now you're preventing uterine cancer and or colon cancer or maybe ovarian cancer, it can be life-saving. Look at this. A case that was referred to me by the GYN clinic here, and so the is in progress. I don't know if you have the answer. So this is where IHC can potentially help. 40-year-old with endometrial cancer. So normal age of endometrial cancer is 61, 62. This is 41. Makes us think hereditary. Doesn't mean it is. The very nice gal came to my office. We did a brief. She knew the name of everybody. 77 people we went through. There's no cancer reported, except for a cousin who, just out of the blue, was just diagnosed with colon cancer. And he, I think, is in his 40s also. So is there Lynch syndrome going on here? I don't know, but I don't know. We took the time to look at 77 people. Who knows what they really died of? We don't know what was going on over there. So we're at MSI by PCR, which is a very reliable screening for microsatellite instability, with aka Lynch syndrome in this case, and IHC. MSI is positive. It moves us. We're still in the ballgame for Lynch syndrome here. We're waiting on the IHC, and we'll get that any day. If IHC is positive, then this person needs to have genetic testing. But and we'll have to figure out who is going to pay for the genetic testing or do it for free. But we might be able to pinpoint which of the Lynch syndrome genes to test for and keep the cost down. So again, this could be life-saving in this family. How am I doing time-wise? 12:30. Okay, good. All right, so that's really, everything I just told you is pretty much old standard stuff that I've been giving this talk for the last 15 years. But now what's changed? So what's changed is that almost 4 years ago to the day, the Supreme Court started to hear a patent case against Myriad Genetics. Myriad had the patent on BRCA testing. And they certainly didn't want to lose that, but they were challenged that it was an illegally given patent, and you couldn't patent the testing of a gene. So it's a complicated issue, but essentially what happened was Myriad lost the rights to the patent. And similar, thinking for analogy, this is like when Bell, remember that, we had one telephone company, and that's where we used, AT&T phones. And then suddenly the company got broken up, and then crazily there were all sorts of people offering phone service. Sometimes it didn't. They were doing all sorts of advanced things. Phones got much more complicated. It's evolved. We don't think about that now, but the same thing is suddenly happening in the laboratory business testing for cancer genetics. By losing the patents, that opened the door for competition, and then other laboratories could start offering BRCA testing. But then they had to compete with each other for more BRCA testing, so they started to add other genes to panels, and these panels started to grow. And that's why now we're kind of a little bit of a shakeout phase. We have multiple companies offering multiple panels of genes that may have weak associations, sometimes strong, but often weak associations with cancer, all kind of competing with themselves. Competitors, they don't always talk to each other. So you get different results, and because some of their information they feel is proprietary. So we have so what's new? Myriad lost their patent. More labs. These are some of the bigger ones. GeneDx, a new one on the block, which is getting popular in Vitae, and lots of other mom-and-pop ones. The multi-gene panels, and what comes with that is variants of unknown significance, and this is the bane of everybody's existence. I'm a member of the National Society of Genetic Counselors, and there's a listserv of over 1,000 counselors and researchers, et cetera. And they're constantly, I can log on, and at least 5 times a day, there are questions. I just got to check to variation in position 5,603. Does anyone know what that means? And that's all the time. How do you counsel your patient? What do you tell them? And you have lots of different opinions. It's evolving. And unfortunately, it's just, that's what nature has given us, that reality, and we're learning to deal with it. Now, the other thing, so the things that have come up that I want to talk about, time permitting, is starting to do somatic testing of tumors. So we're not just testing blood or the saliva for variations that we were born with that predispose to cancer, but we're going to shift to, well, you weren't born with that, but your tumor has it. So we know what you were born with. We know what the tumor has because that's going to affect how we treat you and to take off. And I want to talk about PARP inhibitors and then luck hypothesis, which we talked about earlier, Dr. Vogelstein's hypothesis. This gal should, in my opinion, get the Nobel Prize. Mary Claire King. She's at the University of Washington in Seattle. She's attributed as the discoverer of the BRCA1 gene. Discovery then got taken over by Myriad Genetics, which started commercializing the test and then patented the testing, to her horror. But she's been spending her whole career looking for other causes of genetic cancer, because we know that from those slides earlier, BRCA1 was not the only cause of breast cancer, ovarian. And then she was part of the teams that found BRCA2. And we had more people who were discovered to have a genetic cause. And then, but then there was still a minority of people. Even families with lots of breast cancer and ovarian, there are going to be families where there was no obvious cause. You knew something was going on. You didn't know exactly what. So this is about 10 years old, but they started checking for other genes. They have an inventory in their freezer 10 years ago of about 30,000 families with no known cause. So they said, well, when this new technology came out, next generation sequencing, where you can check for other genes not laboriously and much less expensively, said, well, let's check for CHEK2. But for CHEK2, TP53 is what's Li-Fraumeni syndrome, which historically thought is very rare, and you're going to pick up because it causes tumors in children, such choroid plexus and adrenal cortical tumors in children, etc. But so let's check for these two. And they found when they started opening up to other genes than BRCA1, 2, but to CHEK2 and 3, they found that they were finding more mutations that could be held responsible for these families. So you went from maybe you could find the answer in their lab in 12% previously to maybe 15%. So at one level, that's a big increase. You went up by about, I don't know, a third, but in the other, it's only like a 3% increase, absolutely. But this was the start, particularly at losing its patent panel to multi-gene panels. In fact, when Mary King's lab started offering this to families, Mary tried to block them from BRCA1 and BRCA2, even though she had discovered the gene. So they did this, they ran this, but they had to mask the results for BRCA1 and 2. They couldn't report them out because of patent infringement. But that all went out the window. It's crazy right now. So this slide is from 10 years ago, but really it's not that much different now. Even so, where it's about breast and ovarian cancer familial risk, a lot of families, we don't know the reason. Again, is it environmental? Is it environment plus gene? Is it we're just not testing enough genes? There are more and more genes. Is it rare variations in genes that one family has and another family has a different rare variation? We don't know. We're trying with the multi-gene panels, we're kind of increasing this part of the pie, but at the end of the day, there's a lot of genetic dark matter. We don't know. It's an evolving concept. It may be that one day all of it's genetic. Or we may just be stuck right over here. We don't know. So genes tested means variants of unknown significance. And I have my own rule. I made it up. It's called the Taubman 1% rule, which basically says that if you check for 3 genes, you have about a 3% chance of getting a variant of unknown significance. And if you check for 36 genes, you have about a 36% chance of variants of unknown significance. That's just a curveball that Mother Nature is throwing us. Doesn't mean you should or you shouldn't check for those genes, but you probably, if you're going to do panels, you may want to stick to the panel that makes sense for the cancer you're looking at. So if you're looking at, because some of these panels check for every known association with any cancer, there could be 60 or 70 genes, and even though you started looking out for the cause of a person's colon cancer, you may end up with a variant in a gene that is associated in the literature with melanoma, occasionally pancreatic cancer. We don't really know how often that happens. And now you have to explain it to the patient. And so don't do it, or do appropriate panel, or at minimum, warn the patient, which is what I do every time. And I don't think a lot of people who just do who order genetic tests, and that's fine, forget to warn the patients ahead that they may have variants of unknown significance. And what I say is that there's a, when we order this profile, we may have a 10% or 15% chance of finding cause of the cancers in your family, but we may have an equal chance of having a variant of unknown significance. Don't be alarmed if we find a variant of unknown significance, because it usually means nothing. It just means we don't have enough information. We haven't accumulated enough data. We haven't seen that variation in enough people to know it's a good thing or a bad thing.
Another question, how much of the crack testing of people from Italy or Greece?
Well, most of the BRCA testing was done on white European ancestry. So you're going to see variations that are based on that. Now, variations in people of Pakistani descent and Indian descent or Afghanistan descent are going to be different. I'm thinking it's probably we have a pretty good handle on it. I don't know.
1 in 40 there, or is it less?
We'd have to look it up. I don't know the answer. I suspect now the 1 in 40 is for people of Jewish Ashkenazi descent. It's 1 in 400 to 1 in 1,000 for anybody else. The Italians are more to 1 in 500s, and the Brits more to 1 in 6. I don't know the answer. The VUS, what I call the VUS challenge. This is our genome. This is crazy, but we have 3 billion letters in our genetic code. Every in our body, other than red cells, which gave up their in their evolution, but in every cell in our body, essentially, we have 3 billion bases. And in lifetime, we have, I looked this up, we have 10,000 trillion cell divisions in our lifetime. Every one of those 10,000 trillion times, billion bases have to be copied, and it's got to be done right without any mistakes. That's the miracles of life. How the heck does that happen? It happens in every one of us all the time. With there are variations. We're all 99 to 99.5% identical genetically. There are differences. We're different heights. We have different eye color, different hair colors. Some people are good at baseball. Some people are good at crossword puzzles. That's what makes us different. Just because there's variation doesn't mean it causes a disease. So start checking for variations, and we know what they mean. We're stuck until we get more data. So variations are bad. So I calculate, this is my rough calculation, there are anywhere from 3 million to 300 million variations possible. It depends on what schemata. Some people say that on average 1 in 1,000 bases are different. And other people say that it's much lower than that. But there's a lot of variation, and that's the challenge, is when these variants come back, do they cause disease or not? And so we sequence people, what's going on, but in public databases, there's only about 100,000 publicly available sequences, so we can figure out what's expected in the population. There are more people than SQL. A lot of these are in private databases of companies that are trying to discover drugs. Now, to the U.S. classification, it's a Wild West right now because the different schemes on even how to name what a variation is and how to interpret it. So now we have a couple of sheriffs in town. About 2 years ago, the American College of Human Genetics and the Association of Molecular Pathology had a big meeting, and they had a lot of focus groups, and they said, let's first agree on what we're going to call these things. So this is the agreed upon schemata that we have variations. We're not supposed to use the word mutation, by the way, anymore. We're supposed to use variation. So it's a variation of uncertain significance, likely pathogenic, likely benign, or benign. So this is labs are now supposed to start using. From what I can tell after much discussion, likely pathogenic is greater than somebody has deemed greater than a 90% chance of being so. Likely benign, likely greater than 90% chance. Practical purposes, if it comes back pathogenic or likely pathogenic, almost everybody in genetic counseling would treat it as pathogenic. It becomes when you're over here. Like, but we're not really saying it's benign, uncertain significance. These will at the end of the day, will be benign or not being pathogenic, but you know which ones, yeah. So we're starting to agree on the nomenclature among the labs. That's the first step. And the labs figure out what to call it. You know, it's an important question. Well, they use computer predictive models. One is SIFT, one is Qualifen, the other mutation taster. You can look these up on the internet. You can actually, and I do this from time to time. If you know the variation, a C got changed to a G at position 5,806 in the NF1 gene, you can put it into this, and it'll predict whether it's pathogenic or not. It's a piece of information. It's a computer prediction. That's one piece of information you can use and they can use. Another important thing is called ClinVar and other databases, where somebody has actually put in the pin history or the family history to try and correlate. You know, we had this certain variation, and in this family there were 5 people who had cancer, and 4 had this variation. That adds to the weight of evidence that it's significant. But at the end of the day, each lab independently makes their own mind as to what to call it, and the labs do not always agree. And so what do you do with the information? Well, it's not only whether a gene predisposes you to cancer, it's how likely is it, because even with BRCA, when we talk about time risk of 85% breast and 40% ovarian, not everybody gets those cancers. That's called strongly penetrant. On the other hand, we have things like CHEK2, ATM, RAD51. They're at moderate risk. That's 2 to 4%, 2 to 4 times increased risk compared to the general population. Well, you know, Eric is seeing people on a daily basis who, based on their pathology or their breast density, are already at biopsy results already at 2 to 3 times the risk of the general population. So this doesn't always add that much more information. The patient may already be at that risk, at least from a management point of view. Some genes that I don't even know what they are, AXN, GREM1, XRC22, we're far away from knowing what to do with that. That's a good question. So what do you do? We talked about this earlier. The de facto standard of care, I think, is the NCCN guidelines. The NCCN guidelines, I understand them, were excellent collaboration between the major cancer centers in the United States. Holy Cross, I'm sure, is one of them. And they come up with very, point-by-point guidelines. If this, then that. If this kind of cancer, then that. Do radiation, then chemo. Chemo first, radiation, whatever. But now put together, I don't even know how, groups of people who are vetting these mutations and the data, and they're coming up with recommendations. So this is the kind of new de facto standard. And the good news is they seem to be updating it on a regular basis. So if you go on to NCCN guidelines, and this one was as of 2 days ago, version 2.2017, and you can go down this. You can see the recommendations for all they're saying you should do. And it's going to change. You have coverage. So the question before we started, from Mary said, I heard about a patient with CHEK2. What are we supposed to do? Well, here's what the NCCN guidelines say right now. They say, first of all, no increased risk of ovarian cancer. Whether or not, will be true. But that's what they're thinking right now. Annual mammogram, screening, consider breast MRI with contrast, age 40. Reduction, mastectomy, evidence insufficient, managed based on family history. You can kind of do what you want, but you got some. If 3 people in the family have died of breast cancer, you may for that. If nobody had breast cancer and you don't want to have your boobs removed, you can go by that. and it goes on, down, and down. So I see NCCN guidelines are very good, and I recommend that for this as well as management. And these lines all here in this PowerPoint as of 2 days ago. One of the most interesting, I never would have thought about this 10, 12 years ago when I got into this, but testing of tumors. Why are we just testing your predisposition without testing the tumor? And that is really starting to take off. And I know our oncologists are using it. I know it's expensive. I know there are all sorts of issues that were being constrained by insurance. But this is a patient in my primary care practice that I just speak volumes. So this is a patient of mine who bizarrely ended up with a toenail that fell off and kept falling off, and it wasn't growing right. And after a year, basically, he had surgery to do it, and it didn't look right, and they took a biopsy, and lo and behold, he had melanoma of the toe. So he's been on a 5-year journey, and he had toe amputated. Okay, that's one after it. He had lymph node dissection, which I call was negative. So, it's gone that route. Then he showed up with small met in his lung, and doesn't like the idea. He is a researcher and very entrepreneurial and has his own biotechnology company. So he liked the idea of having anything in his lungs, so he had that removed. Then another one came back, so he had that removed. Another one come back, and he convinced this is not necessarily all in sequence, he removed. He was at the NCI, and he had infusion, Dr. Rosenberg's group of genetically engineered lymphocytes to go after his melanoma, which is very, very toxic, almost killed him, but it did reduce the size of his mets, seemed to be doing something that didn't eliminate it. Then along came BRAF inhibitor treatment. He got on that. That made him sick, but he kind of survived. Then recently they added immune checkpoint inhibitor blocker. Everything would kind of tamp it down, but not quite get rid of it. And then he ended up at Sloan, and they started him on chemotherapy, which kind of helped, but not totally. Along the way, he, I think at Harvard or Dana-Farber, somebody sequenced his tumor genetically to see what was going on there. Hold on. Behold, he has multiple extracopies of the HER2 gene in melanoma. Now, HER2 is a gene that's amplified in breast cancer, that in melanoma, but his tumor has multiple copies. It's really unstable. He has multiple copies of the HER2 gene. So he said, well, what can we do? He said, well, we can give you this new drug. I call it Kadeza, TDM1. I'm not sure. You guys probably know better than I. But it's the newest drug for HER2. It targets the HER2 pathway. So you'd have to be in a study for it to be covered, for it to get it, because no insurance company will cover it for melanoma. Study of this drug in melanoma, because it's all in breast cancer. You know what? I just sold my biotechnology company. I made a few $1 million. Let's do it. So he's paying, I don't know, $50,000, $100,000 a year for this off-label drug. And get tumor shrinking. He feels great, getting better. Why? Because there's a genetic cause in his tumor, and there's a pathway that can be targeted. And all the treatments were kind of peripheral to that. Whether it's going to last for him, I don't know. Whether he's going to have other mutations, I don't know. But this is why somatic testing is taking off. And then another thing that's come out there called PARP inhibitors. So remember at the beginning that cancer is a disease of our genes. That's what I said from the beginning. And the tumors have a lot of mutations in them. They have hundreds or thousands of mutations in the individual tumors. They're very genetically unstable. The cancer cells are kind of a little weird. Like, they have so many mutations, they've acquired these crazy characteristics, like they can not die. They can multiply, but they're not subject to apoptosis, so they hang around longer. Or they travel from their original site, the kidney, to the lung, which they didn't have before. All these mutations that have given these qualities, but like on the verge of dying because they're so genetically unstable. PARP inhibitors do is they make them even more unstable because the body has ways to repair DNA. The BRCA genes we think are important because they maintain genetic stability. They find damage and they fix it. So damage managers are themselves abnormal birth. You don't have that tag guy to go around and to find genetic damage and repair it. But that's the only system in the body that finds and repairs genetic damage. The minor system that has to do with PARP. And what some smart people said, why we inhibit the secondary repair mechanism and make the tumors so unstable that they'll just fall under their own weight. And those are called PARP inhibitors. And PARP comes from poly-ADP ribose polymerase. So it makes them, what's neat about them, it can be taken as a pill, at least most of them that I'm familiar with. They're well tolerated for the most part. I'm sure they have side effects that my oncology colleagues know about. They can take people who have, they were first developed for people who have BRCA mutations that have cancers from them to treat it. You already have a BRCA situation in these cells, so they already can't repair a lot of genetic damage. And we're going to take it one step further. We're going to knock out the other mechanism. So we thought it worked just for BRCA mutations. That's how it was designed. And it turns out it works best. These drugs work best in people who have ovarian cancer, for instance, and have a BRCA mutation. But it turns out they're working as well in people who don't have BRCA mutations, but not quite to that extent. So we're going in a new direction. We're actually trying to make cells even more genetically unstable to kill them. And then finally, from the beginning, if somebody has cancer, it's cancer in their family perhaps, and it's not due to a known genetic mutation, and it's not due to the environment, what's it due to? And then I have Dr. Bert Vogelstein at Hopkins, who published an article saying it's bad luck. And what he basically is saying is that we have all these trillions of cell divisions in the body going on all the time, and we have a very robust spell checker system, BRCA, PARP, etc., that 99.9999999% finds mistakes and fixes them. But after all, a mutation is going to slip through, just because, like a cosmic ray or something. And then you get one mutation, it makes you a little bit more genetically unstable. Then you get another, and next you have a whole cascade and you have cancer. It's interesting, and patients that the reason may be it's just bad luck, and a very bright person who may get the Nobel Prize has gotten a lot of pushback for it, by the way. But I think there is something to that. The pitch for being on the lookout for cancer syndromes, genetic counseling, and or testing. This is a study that was done about 10 years or so. It said 11.4% of patients at a mammography center have family history that indicated a substantial probability for a significant genetic mutation, but less than 3% of people were actually sent for genetic counseling. We need to do a better job there. This is primary care like myself. family history of cancer in 63%, age of diagnosis only asked in 51%. So, it's not enough to, when you're doing all the things you do in primary care, and trust me, there's a lot, is there any cancer in your family? That's not going to get you where you want to know. You have to think patterns. Oh, there's colon, what kind of cancer? Colon cancer. Oh, was it age? 45. Anybody with uterine cancer? You have to answer those kinds of questions to get there. Women don't go for genetic testing. A lot of women don't want to go for it. It's a battle. The doctor didn't suggest that that's the number one reason that they don't go for it. The doctor didn't suggest it. Expensive, and I heard my insurance won't cover it. Tests, when I started, were $5,000. Go down to the list price is $1,500 for these panels, and these labs will do it for $475. Most people who live in Montgomery County, that's two cable bills. They can afford it if they want to. But there's a lot of shtick with getting cancer genetics. Some people don't want to know, and I respect that. If I'm positive I lose my health insurance, it's not true, at least unless it gets repealed. There's Genetic Information Non-Disclosure Act. It's the Non-Information Act. That's been on the books for over a decade. You cannot be discriminated in health insurance due to genetic results. And even you can be discriminated because you have breast cancer. Okay? Now, you could be discriminated potentially for disability or life insurance. That's not covered by GINA. I'll have to have my breast removed. Well, we know that even if we know you're genetically predisposed, you have other options. You can be closely watched by Dr. Urishkin. Why doctors don't do it? It's expensive. Insurance won't cover it. Well, we talked about that. Now, this is one. You already had cancer. What difference does it make? Well, some truth to that. I mean, you already have breast cancer. You're going to be watched like a hawk. I understand that. But what if you're at risk for ovarian cancer, which is deadly, can rapidly develop, and for which no screening for it? Maybe you need to get your ovaries removed. Well, we need to test you to find out perhaps if you need to go there. Ashkenazi. Some doctors think that they get confused because when BRCA testing started, it was really found initially in people of Jewish descent because that's how they confined it, because there were 40 Jews were walking around with these mutations. It was easy for Mary Claire King to figure out what was going on when you had a lot more people with that, but that's not true anymore. And I say, just because the patient has been to the best cancer place and treated their cancer, don't assume if you're in primary care or oncology that anybody ever asked the question, why did you get the cancer in the first place? People in the best places, they get treated, they do well, but nobody ever asked, like, let's look at your family history. And people assume because they've been to these places that it's been done. It's not always. Not always. Then think about patterns. Breast ovarian pattern, colon uterine pattern. For the CDUK2 name, I found 2 people in my own primary care practice who have this mutation where it exposes to multiple melanomas and pancreatic just by asking questions, convincing them to be tested. And now one of them is going for yearly MRI of the pancreas in the hope that if they come down with pancreatic cancer, we're going to catch it. So I calculate that in the average primary care practice of 2,000, there are 14 BRCA patients. So how many can say that we know who those people are? We're not doing a good job of screening. And I would say for HNPCC, there are 2. And in the case of medullary thyroid cancer, these are rare cancers, but that's associated with the with that 2 mutation. Pheochromocytoma, particularly in somebody less than 50, you may have a 25 to 50% risk of having an actionable mutation. Adrenal carcinoma, ditto. And then, so for a question. So this is my little personal story, which I don't share. So here I am about 6 years ago in the lab of Mary Claire King, which has showed you, I think is going to get the Nobel Prize or should get it. We happened to be on vacation in Seattle, and I knew she was on the University of University of Seattle, University of Washington campus in Seattle. And I said to them, I didn't know where Mary Taylor King's lab is. And they said, oh, it's right over there. So we walked in. They said, we're Maryland. We happen to be here on vacation. Like, we'd like to meet you. And this is the analyzer they were doing their stuff on and ended up publishing that paper. So why did I get into this? So here I am, 6 years later. I had a little less gray hair. This is my wife, Nancy. At this point, Nancy is a 6-year survivor of ovarian cancer. She's now a 13-year survivor of ovarian cancer. So what's her here? Nancy's aunt died of ovarian cancer at age 54. The other aunt on the same side died of breast cancer at age 54. And Nancy had ovarian cancer at age 52. You think there's something going on here. What did I learn about screening for ovarian cancer? Well, the year before she was diagnosed, we were on vacation, and she had a little abdominal pain in her right upper quadrant. They said, sounds like bladder to me. So when we come back, let's do a sonogram of your gallbladder. I said, you know what, your aunt had ovarian cancer. Why don't we do a pelvic ultrasound at the same time? So her gallbladder was fine. They said, oh, everything's fine. You have a small cyst in your left ovary. So why don't you back and we'll check it in 3 months. She came back 3 months, cyst gone. I said, great. A year later, she had a cough that wouldn't go away. After 3 months of, as you can imagine, a doctor giving, every possible medicine, try that. We got a chest X-ray. Half her right lung was filled with fluid. Paracentesis, she had 2 liters of fluid taken out of her lung. We thought pleurisy. Said, let's see what happens. And then 2 days later, the pleural effusion came back. She's otherwise fine. We said, okay, why is there? What's gone? Because the pathology of this was negative. So we said, well, let's do a CT of your chest and your abdomen. Her chest actually was fine, other than a effusion. She had a 6-centimeter mass in her ovary. And at surgery, right here at Holy Cross, she had 6 liters of ascites within of a negative, really 2 negative sonograms. Ovarian cancer is kind of a cancer. It comes out, it's very aggressive. You can't screen for it. If there's a genetic predisposition, you want to know about it ahead of time. We were on the fortunate side. But her genetic tests were negative. So we don't know. Talk to Nancy. Questions? How is she? Right. Got her right now, and usually aches and pains in their knee and whatever, like everybody else. Yes.
Are you recommending that we order both tests on colon cancer? What do you think?
It has to do with resources. You've got, from my point of view, I'd like to see both tests. Because sampling errors with this stuff and procedural in doing the test, I like to do both. If you say I can only do one, do the IHC, because that helps you pare down which genes to look for. And then it can go another step further. If it's the H1/PMS2 due to hypermethylation, which is a genetic epigenetic change, which is not genetic. But then there are things like BF from promoter hypermethylation. I'd like to do both. If you pin me at all, I would just do the IHC from a reliable lab. You have to remember that I had a case not that long ago where a patient, they went for the colonoscopy, saw what looked malignant. They took the biopsy. It was cancer. They did the IHC. It came back negative. no sign of genetics. The family history was not particularly suggestive. This person really wanted to know why they got colon cancer. Happy. So he came back to me. I said, I know, but you know, they took a little snippet at the time of your colonoscopy. It's not, you know, they may have missed something. So I said, at the specimen that was done, operative sample. And so we had the lab do that. I think it was here at Holy Cross, perhaps. He did that. He did have Lynch syndrome. And it's just that when they did it on the colon part, the piece of tissue, in retrospect, they reviewed it, was normal colonic epithelium that they had tested. It was just a millimeter or two away. So I'd like to do both, but otherwise, if you do one IHC, the question is what age. If you've got resources, you've got your grant, whatever, do it on everybody. But practically, most people are doing it on 50, 60, and below. That's where your highest yield, much higher yield is going to be. Yeah. Question? So with the big one, I mean, obviously the reps are going to come in and say they're best, they're great, and they're going to try and cut you a deal. And that's fine if you test more people. I think they should all be CLIA certified. You wouldn't want to deal with anybody who's not CLIA certified. I don't think any of us would knowingly do that. The ones that have been around the longest, you know, the ones that have been around the longest are probably the ones that, you know, genetics is that it's variable. I mean, if you do that sample, you're going to get the same result. You should get the same result all the time. There was the label changed, something like that. I mean, those things can happen, but the real issue is the interpretation of the variants. But I mean, things can happen, and hopefully they don't. A lot of this is automated. I mean, I'll tell you, I had a family not that long ago where they have a CDH1 mutation, which leads to gastric cancer, and the only treatment for it is to remove your stomach. That's major. And I had this kind of drove me crazy, but I had two people, family, young, in their 20s, in their 30s, 40s, two cousins came in to see me, and we ended up doing all this, and we tested them both, which I was nervous about because I didn't like the idea of having them both in the office, getting samples, whatever, but we did, and one of them turned out positive. And one of them was likely going to end up with a gastrectomy, and the other one not. And when I saw that, I could sleep for 2 weeks because I wasn't sure, maybe is it possible we switch the samples. I had one come back and be retested by himself just because that wouldn't happen. But they should be liable. I think it's the issue of interpreting the variants and how robust those reports are. Sometimes I'll get a report from one lab and I'll call up another lab and kind of pimp them for information.
DNA editor called CRISPR, and if I understand it right, it has the ability to seek, identify variants, to nip and replace. Sort of the way of the future.
You know, 20 years from now, and some of these people, in theory, if you have a BRCA mutation, you could, you want to have children, you could have a test tube embryo, and you could go in and find the mutation and fix it. If we're not there, not going to be there for a long time. But thank you very much.
Thank you.
Thank you.
Thank you for taking the time. We really appreciate it.
Well, thank you. Thanks for having me.